Welcome back to the deep dive. Today, we are undertaking a custom, really high stakes deep dive into one of the most demanding engineering challenges I've seen in a while, and it's in the heavy commercial vehicle sector.
It is, and it involves concrete, which, when you think about its chemistry and just how you handle it, it feels almost specifically designed to destroy sensitive electronics.
That's a perfect way to put it.
Uh,
We aren't looking at a high volume passenger EV or some kind of standardized fleet vehicle today.
no, not at all. We are dissecting the Engineering Technical Specification, the ETS, for a really specialized piece of hardware. It's destined for a P2 hybrid cement mixer truck. And that environment, well, it dictates absolutely everything.
Okay, let's unpack this mission a bit. We're here to really understand the requirements for a high reliability DC to DC converter. So this is the unit that's responsible for taking that 400-volt high voltage power from the traction battery
Right.
and stepping it down to the 24-volt low voltage system that, runs all the truck's auxiliary functions. I think the average person, even someone in the industry, probably thinks of a DC-DC as just a glorified power brick, right? Not that
Oh.
critical.
And that is precisely the dangerous misunderstanding we need to correct right from the start. Our core thesis, and this is drawn directly from the engineering requirements, is that in this specific application, the DC-DC is not an auxiliary power module at all.
Okay.
It has to be recognized, designed, and tested as a safety-critical, long-duration, heavy-load energy conversion core.
That's a huge identity change. So you're basically arguing that this DC-DC needs to be treated with the same rigor as the main traction inverter, the massive power ECU that actually drives the wheels.
Exactly.
So why the elevation? What makes this specific piece of hardware suddenly ASIL rated and absolutely mission critical? In a normal car, if the DC-DC fails, you might, lose your radio?
It all comes down to the consequences of failure. The catastrophic consequences within the duty cycle of a cement mixer. You have to think about the operational profile. The engine is often off, or it's idling at a very low RPM for, long duration, sometimes hours.
Right, while it's waiting to unload or just crawling around a construction site.
Exactly. And during that time, the entire vehicle's essential operational equipment, the safety equipment, it's all running solely on that 24-volt supply, which is fed directly and only by the DC-DC.
So what are those essential systems on a big commercial hybrid truck? The ones that absolutely cannot be allowed to fail?
We've identified 4 key systems that create this cascading failure scenario. First, the 24-volt supply runs all the vehicle's electronic control units, the ECUs,
Yeah.
the brains of the truck.
Okay, so if that drops, the whole vehicle control and diagnostics network is just gone.
It ceases to function. And second, and this is maybe the most critical for the high-voltage system itself, you lose the auxiliary cooling system.
Which means those really expensive 400-volt components, the battery pack, the traction inverter, they immediately start to overheat because their dedicated pumps and fans are all 24-volt driven.
Precisely. So you've now severely damaged the most expensive systems on the vehicle. But the third consequence, and this is the most financially dramatic one, it relates directly to the product the truck is carrying,
The mixer drum?
the mixer drum rotation control.
So the drum just stops, and that's a clock ticking.
If that 24-volt power fails for any extended period, the concrete inside the drum begins to cure. It hardens. And that isn't just a simple breakdown that, requires a tow truck.
No.
That is the instant destruction of the vehicle's entire payload. We're talking potentially tens of thousands of dollars worth of construction material turned into a solid, useless block of scrap inside the truck. The operator is now facing a massive logistical nightmare, maybe even a total loss of the truck, all because of a failure in what was, historically considered just an auxiliary component.
That commercial risk, and you tie that to the immediate loss of systems like steering assist and braking control, it makes the case crystal clear. This is a component that's fundamentally tied to safety, to operability, and to, preserving the asset itself.
Exactly. And that combination, severity, exposure, and controllability, that is what mandates treating this DC-DC with the rigor of an ASIL-rated Power ECU. It's the heart valve. It's controlling the lifeblood of the entire control and cooling system.
And this is where it gets really interesting, because this specialized high-stakes identity is all driven by 4 unique and, frankly, brutal challenges that only this cement mixer environment presents. So before we get into the engineering solution, what are those 4 pillars of extreme challenge that the design team has to account for?
You really need to picture the job site. It's essentially a zone of maximum environmental hostility. The 4 pillars are 1. Sustained heavy electrical load. This DC-DC has to maintain, often, greater than 70% of its rated continuous output for hours.
Hours. That's way beyond a typical automotive duty cycle.
Far beyond. 2. Extreme contamination and corrosion. It has to survive this incredibly invasive cement dust, which is hygroscopic and corrosive, plus routine high-pressure chemical washdowns.
Okay.
3. Poor thermal conditions. You have minimal natural airflow because the vehicle's moving so slowly or just idling for long periods, combined with those heavy, continuous loads.
A recipe for overheating.
And finally, number 4, intense mechanical stress. We're talking sustained, high-amplitude vibration from driving on unpaved roads and the constant rotational dynamic forces of that heavy drum.
That sets the tone perfectly. This DC-DC is being asked to survive a structural, thermal, and electrical gauntlet that a component from a passenger car. Well, couldn't even dream of it. So let's move into defining that environment in more detail, starting with that first, most demanding requirement, the sustained load profile.
Right. You cannot size the DC-DC based on average power draw. It has to be sized for continuous high demand. In a passenger vehicle, even something powerful like an ABS pump drawing 100 amps, that's momentary. Milliseconds, maybe a few seconds.
But here, the load is long-duration continuous power. We're talking about the DC-DC having to output more than 2, 3, or even 4 kilowatts sustained.
Exactly.
And the sources itemize where those constant draws are coming from is all the auxiliary equipment that's been aggressively electrified in this hybrid architecture.
That's right. If you look at the auxiliary drives that you need to maintain the hybrid system, you have electronic water pumps for the high-voltage cooling loops,
Yeah.
pulling 20 to 40 amps constantly.
Okay, that's a baseline right there.
Then you have the heavy-duty cooling fans for the battery and the power electronics, which can pull another 30 to 60 amps. And those run whatever the HV system temperature says they have to, regardless of whether the truck is moving or not. These are completely non-negotiable systems.
Right, they're essential for the hybrid architecture's survival. But then you've got the big dynamic load, the electronic hydraulic power steering, the EHPS. That's the load that really defines the absolute peak sizing requirement, isn't it?
It is. It's the moment where the system is pushed right to its limit. The EHPS pump requires a massive peak current, often between 80 and 120 amps, and sometimes it'll spike even higher.
And crucially, in a mixer truck that's maneuvering slowly on a dusty site, the driver might be turning the wheels lock to lock over and over, or just holding a turn for an extended period.
Which means that a 120 amp draw can be sustained for much longer than in a passenger car. We're talking maybe 30 seconds or more. If the DC-DC can't handle that, even with the 24-volt battery helping out, the steering assist fails. And again, that just raises the functional safety stakes significantly.
So it's a continuous load machine that also has to withstand these huge momentary surges. That's the electrical challenge. Now let's pivot to the physical gauntlet, because this is where the cement mixer environment becomes truly unique. That intersection of contamination and mechanical pounding.
Let's start with the contamination. Cement dust is incredibly fine and highly invasive. Chemically, it's got silicates and high levels of calcium oxide. It's also hygroscopic.
Meaning it just pulls moisture right out of the air.
It readily absorbs it. And when this dust inevitably mixes with water in a wet construction site, it forms this alkaline hardened crust.
Which is definitely not a protective crust for the component.
No, this crust is a complete nightmare. It clogs any potential air cooling fins. It acts as an aggressive electrolyte, which accelerates corrosion on any exposed metal. And worst of all, it breaches conventional seals. It finds these tiny micro gaps and then it hardens, acting like a wedge and potentially compromising the integrity of standard gaskets and cable glands.
And then after enduring this alkaline, dusty environment, the vehicle is subjected to its brutal cleaning regime.
Exactly. The final act of abuse is the necessary washdown. To prevent all that accumulated cement from hardening on the truck, it's cleaned daily, often using high-pressure, high-temperature water jets. Sometimes they're even combined with mild acidic solutions to dissolve that alkaline crust.
Which means the DC-DC unit can't just be, say, IP67 sealed. That's just for dust and temporary submersion.
That standard isn't even close to good enough. The connectors and the housing must meet the incredibly rigorous IP6K9K standard.
IP6K9K. For listeners who haven't run into that before, what does that standard really imply in practical terms?
IP6K9K is the industry standard for resisting a high-pressure, high-temperature wash. We're talking about surviving water jets delivered at a pressure of up to 100 bar.
Which is immensely powerful.
And at a temperature of 80 degrees Celsius, often from close range and from multiple angles. Designing a unit to resist that kind of sustained thermal and kinetic stress is far, far harder than just designing one to sit underwater. It demands really specialized materials and connector systems.
Okay, so now let's combine that chemical and thermal assault with the physical pounding. The mechanical stress profile for a cement mixer, as you mentioned, is way beyond a normal heavy-duty truck.
This is where the numbers really give the clearest indication of the required durability. Standard heavy commercial vehicle vibration testing, like what's referenced in ISO 16753, is already tough. But because the mixer truck is constantly on unpaved roads, navigating deep potholes, and it endures the sustained rotational dynamics of a loaded drum, the design target for random vibration is just pushed to the extreme.
And what is that design target? What's the root mean square acceleration, the ARM?
That the ETS mandates a design target of 5.8 grams.
5.8 grams. That sounds astronomical. Can you put that into context for us? How much higher is that than typical requirements?
Well, a standard passenger car might be designed for, say, 1.5 to 2 grams. A typical long-haul highway truck may be in the 3 to 4 grams range. This 5.8 grams requirement is significantly higher. It represents a continuous high-amplitude, multi-axis shaking. It's like constantly driving over extremely rough terrain.
So this isn't about surviving one big bump. It's about surviving constant, violent motion over a 10-year, 300,000-kilometer lifespan.
And to prove it, the sources specify that the testing involves subjecting the unit to 32 hours on each of the X, Y, and Z axes under those random vibration specs. That duration, at that intensity, is purely designed to accelerate component fatigue and find every single weak link in the physical structure. It's targeting the mechanical lifetime of everything. The solder joints, the housing welds, the connections between the cooling plate and the PCB, everything.
This inherent violence brings us right to the cooling conundrum. With that massive electrical load, the low-speed operation, and all that environmental dust, air cooling is a complete non-starter, correct?
It is a guaranteed recipe for thermal failure and premature system shutdown. I mean, consider the 3 thermal strikes against air cooling. First, low vehicle speed means minimal ram air for convective cooling.
Right.
Second, the truck is often idling or just crawling on site, generating maximum thermal stress internally. And third, that cement dust would immediately clog and insulate any air-cooled fins.
So the DC-DC would quickly enter thermal derating mode, which could lead to the loss of 24-volt power just when the truck is under maximum operational stress.
Precisely. The conclusion is therefore non-negotiable for a high-power safety-critical unit like this. Liquid cooling is mandatory. The DCBC must be a sealed, plate-cooled unit that's integrated into the vehicle's dedicated low-temperature fluid loop to ensure you get stable, long-duration output, regardless of the ambient environment or vehicle movement.
That continuous demand and punishing environment really set the stage for the most strategic component decision. This leads us to Section 3, the strategic technology decision. The 400-volt platform gives the engineering team a choice between traditional silicon power devices and the more advanced Silicon Carbide, or C MOSFETs. Given the unique blend of electrical, thermal, and mechanical hostility we just detailed, how does the initial cost of CEC stack up against the long-term reliability required here?
This is a classic engineering trade-off that, for this specific application, it moves from just a simple cost-efficiency calculation into a really strategic reliability decision. While SiC components definitely have a higher initial material cost, sometimes 1.5 to 2 times that of high-performance silicon, the total system cost of ownership, the TCO, the calculation, heavily favors SiC.
Okay, let's look at the electrical and thermal numbers first, since that's usually SiC's main benefit in most applications.
Right. Traditional silicon power solutions, using robust MOSFETs or maybe IGBTs on the 400-volt platform, they typically offer peak efficiencies in the 92 to 95% range. And while that's respectable, it results in significant thermal loss.
Okay.
So if the DC-DC is outputting 3 kilowatts, the wasted heat, the thermal loss, is around 150 to 200 watts. That's a huge heat load that has to be actively managed out of a small sealed box.
And SiC, leveraging its superior bandgap properties, what does that do?
SiC dramatically changes the equation. Because it has near-zero reverse recovery charge and much lower switching losses, it can achieve peak efficiencies in the 95 to 97% range.
Right.
But more critically, that thermal loss for the same 3 kilowatt output drops to between 60 and 90 watts.
Wow, that's a massive reduction. Over 50% less waste heat right at the source.
And that's the key so what on heat. In a liquid-cooled system, this reduction directly translates to a smaller, simpler, and inherently more reliable cooling system infrastructure. Less heat means you can get away with lower fluid flow rates, smaller internal cooling plates, smaller vehicle heat exchangers. The whole system is just far more robust against high ambient temperatures or, say, temporary blockages in the cooling loop.
It dramatically reduces the risk of thermal deteriorating and improves the overall lifespan.
Yes.
But, as you pointed out earlier, the true strategic argument for investing in C for this specific truck isn't just about efficiency or cooling, it's about mechanical durability under 5.8 grams of vibration. So how does an electrical semiconductor choice solve a structural engineering problem?
This is the crucial and often overlooked connection in power electronics design. SIGL's superior material properties allow the engineers to dramatically increase the system's switching frequency. Traditional silicon MOSFETs are limited, maybe to the 50 to 100 kilohertz range because of thermal constraints and switching losses. SIG's, however, allows the design to push the frequency up to 150 kilohertz and optimally into the 200 to 300 kilohertz range.
And why is that higher frequency so desirable?
Because the physical size of the inductive and magnetic components, the transformer, the inductors, the filter chokes, is inversely proportional to the operating frequency. By doubling or tripling the switching frequency, the engineering team can reduce the physical size and, critically, the weight of these heavy magnetic components by 40% or more.
So, if I'm visualizing it right, instead of mounting a component the size and weight of a full paperback novel, the design only needs to secure something that's closer to, I don't know, a pack of playing cards.
That analogy is perfect. Lighter components have less inertia. Under that sustained 5.8 grams vibration profile, a heavy transformer acts like a small hammer, continuously exerting massive inertial forces on its own solder joints and the underlying PCB traces. By making that component lighter, you drastically reduce the mechanical stress on the PCB interface.
That makes the SEC adoption a strategic investment for mechanical reliability, not just an efficiency upgrade. It's actually an anti-vibration architecture.
Absolutely. The higher frequency is the design mechanism that reduces mass, which in turn fundamentally increases the fatigue lifetime of the PCB solder joints and component mounting under extreme shock and vibration. The engineering decision for this ruggedized 5 kilodual plus DC-DC is really driven by mechanical survival, and it's paid for by the cost of SEC.
So, if the engineering team is weighing the options for different configurations, what's the final recommendation on power technology based on the desired continuous output?
For lower configuration versions, which might only need a continuous output of, say, 3 kilowatts or less, perhaps in a variant with fewer electrified accessories, a carefully designed, high-performance size solution with enhanced cooling might still be acceptable, if initial cost is the absolute defining constraint.
But for the mainstream version,
However, for the robust, mainstream, long-duration, safety-critical versions, specifically those requiring continuous output of 5 kilowatts or greater, which is the preferred standard for a maximum reliability ballistic, is the necessary system-level optimal choice. The long-term reliability and the associated fuel savings just make the total cost of ownership lower, despite the higher initial component cost.
that is a phenomenal piece of cross-disciplinary insight using power electronics to solve what is essentially a civil engineering durability problem. Now that we've established the architecture, let's move to the hard numbers in Section 4, quantifying the electrical and power requirements. And we'll start with the high voltage input side.
Okay, the nominal HV input for this hybrid platform is 400 volts DC. However, the operational reality of a heavy-duty cycle requires a massive continuous working range. The DC-DC has to maintain full continuous output from a depressed voltage of 250 volts DC all the way up to 480 volts DC.
That 250-volt floor is truly critical and something you'd often overlook in passenger vehicle specs. Why is it so crucial that the DC-DC sustains full output at such a depressed bus voltage?
Well, that 250-volt floor directly addresses the heavy-duty cycle of this vehicle. When the truck is operating at maximum output, say attempting a very steep uphill climb or powering the main electric motor while simultaneously engaging the high-power mixer drum, the HV battery current draw is just huge.
Right.
And this heavy current pull, combined with the inherent internal impedance of the battery pack in the long bus lines, causes the DC link voltage to sag significantly. It can momentarily drop right down to 250 volts.
And if the DC-DC fails to regulate here, the 24-volt system collapses at the precise moment the vehicle needs maximum power and control to complete a high-stress maneuver.
Exactly. The DC-DC has to employ sophisticated control and magnetics to maintain 5 kilowatts of output, even when the input voltage is nearly 40% below nominal. Conversely, on the upper end, we need protection from voltage spikes. The DC-DC has to be designed to withstand potentially severe transients of 500 volts DC for at least 1 second, covering the substantial voltage surges that occur during heavy regenerative braking.
Especially if the HV battery is near its peak state of charge.
That's right.
Moving to the low voltage output, we're charging a standard 24-volt lead-acid battery system. What are the key output targets here?
The output target is nominally 27.5 volts DC. This specific voltage is chosen to perfectly match the charging curve of the 24-volt battery, which ensures optimal charge health and lifespan. This target also has to be precisely adjustable via CAN communication by the Vehicle Control Unit, or VCU.
And I imagine noise is a big concern.
A huge concern. To prevent noise from corrupting sensitive ECUs, the output ripple must be tightly controlled, specified to be below 300 millivolts peak to peak under all load conditions.
Let's discuss that critical question of output power sizing again, the 3 kilowatt versus the 5 kilowatt. How did the engineering teams justify the 5 kilowatt recommendation?
The sources define two mainstream paths. The 3 kilowatt solution gives you about 110 amps continuous. The 5 kilowatt solution provides 180 amps continuous. The 5 kilowatt option is a robust mainstream recommendation because it provides maximum safety margin and true future-proofing against any accessory expansion.
So it ensures the DC-DC can cover all known continuous loads plus the EHPS peak demand without relying on the 24-volt battery as a crutch.
Exactly.
But that 3 kilowatt solution must be tempting for cost and space optimization. If it only provides 110 amps continuously, how does it physically manage those 120 to 140 amp peak loads from the EHPS pump?
The viability of the 3 kilowatt option hinges entirely on the 24-volt lead-acid battery's inherent capacity and its state of charge. The DC-DC handles the steady-state load, your fans, pumps, control ECUs, typically consuming about 2.5 kilowatts. The battery is then expected to peak shave, the short, high-current pulses. So if the EHPS pump pulls 140 amps for 30 seconds, the 3 kW DC-DC provides 110 amps, and the remaining 30 amp deficit is drawn directly from the battery.
So the 3 kilowatt option is more compact and cheaper, but it introduces a pretty significant operational risk. If that 24-volt battery is depleted or failing, the DC-DC alone cannot meet the vehicle's maximum load demand, which brings us right back to that potential safety failure.
Exactly. The 5 kilowatt design eliminates this operational dependency. It ensures that even if the 24-volt battery is completely dead, the truck can still perform critical functions, including steering assist and maintaining HD cooling. This dramatically reduces the field failure risk.
And we also have to reinforce the stringent efficiency targets that make CC pretty much mandatory.
The specific efficiency targets are set exceptionally high, greater than 97.5% peak efficiency, and critically, efficiency must remain above 92%, even at a 10% load. This minimum light load efficiency is essential because the truck spends so much time idling or just waiting on site where the energy demand is low but still continuous.
And tying this back to the total cost of ownership for the fleet operator.
The efficiency targets are directly linked to fuel economy. When the main engine is idling, the DC-DC is drawing power from the main HV battery, which is ultimately charged by the engine generator. Every 1% gain in efficiency can reduce the overall parasitic fuel consumption by 1 to 1.5% during those high-intensity, long idle mixing operations.
And when you multiply that by a fleet operating thousands of hours a year, the fuel savings alone can rapidly justify that Sunstein investment.
They absolutely do.
Okay, finally, let's detail the control strategy. How does the DC-DC manage all these fluctuating demands?
The DC-DC uses an isolated topology, most likely a high-frequency LLC resonant or a phase shift full bridge, to achieve that high efficiency and galvanic isolation between the HV and LV systems. The primary operating mode is constant voltage, or CV, maintaining that stable 27.5 volt output. However, it must be able to seamlessly switch to constant current, or CC mode, when necessary.
When would constant current mode be required?
Two main scenarios. First, for safely charging a deeply discharged 24-volt lead-acid battery, where you have to limit the current. And second, for dealing with high-inertia, high-surge loads like large cooling fans spinning up. The DC-DC needs to limit its current output to protect its own internal circuitry from those transient stresses.
And what about the safety protocol for pre-charging the system?
Mandatory soft start logic is required every time the unit is initialized. The input capacitors on the 400-volt side are substantial, sometimes exceeding 500 microfarad, to handle the high-frequency ripple. You just cannot expose these large capacitors to a hard switch-on from the HV bus.
It would be a massive current surge.
A destructive one. The soft start ensures the pulse width modulation, the PWM duty cycle, ramps up slowly, typically over 100 to 200 milliseconds, gently pre-charging those input caps and preventing those huge current surges on the HV bus. And furthermore, the unit has to support low-power sleep modes, that KL30 functionality, with sub-1 milliamp leakage current when the truck is parked to preserve the HE battery charge.
With the electrical blueprint defined, let's move to Section 5, where we focus on the extreme physical requirements. Hardening the system. This is where the mixer truck environment really dictates the material science of structural engineering solutions.
Right, so we established that liquid cooling is non-negotiable, but the ETS specifies really detailed operating parameters. The required coolant has to be a 50-50 mixture of ethylene glycol water, or EGW. The flow rate must be robust, generally specified between 6 and 10 liters per minute to ensure maximum heat transfer.
And the temperature management has to be incredibly tight to make sure that SUSI advantage actually pays off.
Absolutely. The requirement often states that the maximum allowable temperature rise, the delta T, across the DC-DC unit from coolant inlet to outlet should be less than 10 or 15 degrees Celsius. This indicates that the internal design, the cooling plate geometry, and its thermal path resistance must be highly efficient. And crucially, the DC-DC has to be integrated into the vehicle's dedicated low-temperature cooling loop shared only with the battery and traction inverter.
Specifically avoiding the much hotter engine coolant loop.
You have to avoid that.
Next, the vibration-resistant structure designed to withstand 5.8 grims. We talked about CC reducing component weight, but how do engineers secure what's left inside that box?
The focus shifts to mechanical reinforcement and dampening. Heavy components like magnetic inductors and large capacitors are still major failure points. Their mass creates huge inertial energy when they're shaken, which concentrates all that stress onto their termination points, the solder joints.
So you need some kind of internal structural bracing and dampening that can handle continuous high-amplitude abuse.
Correct. The first strategy is mandatory partial or even full potting of the TCB using a thermal silicone gel. This specialized gel is non-conductive, and it acts as both a conformal coating and a mechanical shock absorber. It secures the components by converting localized inertial forces, that hammering into distributed compressive forces across the entire body of the component.
So it just locks everything in place, enhancing insulation and vibration dampening.
Exactly.
That protects the components. But what about the PCB itself?
The PCB also has to be structurally reinforced. The requirement mandates a minimum PCB thickness of 2.0 millimeters, which is thicker than standard automotive boards. And it requires local thickening or dedicated metallic support brackets for the heaviest magnetic components. This distributes their load away from the brittle solder joints and directly into the cooling plate structure.
Let's move to external connection integrity. We need to prevent failure where the power leaves the box. You mentioned fretting corrosion as a subtle but critical failure point.
This is a phenomenal detail, and it's specific to high vibration environments. Fretting corrosion happens when vibration causes this tiny micro-movement, we're talking measured in microns, between the mating surfaces of a connector terminal. This movement wears away the protective gold or tin plating, exposing the base metal.
And that base metal quickly oxidizes, leading to increasing contact resistance and intermittent connection failure. A connection that slowly corrodes itself to death through constant shaking.
Precisely. To prevent this, the ETS requires that external wiring harnesses must be fixed and rigidly strain relieved at a point 150 millimeters away from the DC-DC connector. This ensures that the 5.8 grams of vibration is absorbed by the harness structure, not transferred directly to those delicate connector terminals.
Now, the ultimate defense against the exterior environment, sealing and protection. Reiterate the mandatory standard needed to survive that high-pressure, high-temperature washdown.
The aluminum housing itself must be rated IP67, which is, straightforward dust and immersion resistance. But the connectors must meet the much higher IP6K9K standard. This requires specialized connector housings and seal designs just to repel water jets up to 100 bar pressure and 80 degrees Celsius. Without this, the unit would quickly fail from water ingress during routine cleaning.
And what about managing the internal pressure changes caused by the rapid heating and cooling cycles of the unit?
That's where the breathing effect comes into play. As the DC-DC rapidly heats up during high-load mixing, the internal air pressure rises. When it cools quickly, maybe when the truck stops or that high-pressure cold washdown starts, the internal pressure drops, potentially creating a vacuum that sucks in contaminants or moisture right past weakened seals.
So what's the solution?
The solution is a high-performance, Gore-Tex-style waterproof breathing valve, or a breather. This allows the internal and external pressures to equalize freely without permitting the ingress of contaminants like dust or moisture. It just stabilizes the internal environment.
And finally, the choice of terminals must reflect the high current and vibration needs.
Standard plug-in automotive terminals are simply inadequate for 180 amps of continuous current in a high vibration environment. For the low voltage output, the recommendation is mandatory M8 or M10 screw stud terminals. These provide a mechanical bolted connection that offers superior resistance to both vibration and massive continuous current flow.
Which eliminates the risk of terminal wear and ensures robust power delivery, and I assume they're protected by IP6K9K caps.
They have to be.
We have defined a physically hardened, liquid-cooled, high-performance module, but as this is now designated safety critical, that leads us directly into Section 6, addressing the core functional safety and compliance framework, specifically ISO 26262 and EMC.
This is where the consulting rigor really comes in. Since this DC-DC is the sole energy core for all control and safety systems, it requires strict functional safety goals, known as ASIL Automotive Safety Integrity Level. The core DC-DC unit targets ASIL B.
But you mentioned that this level can escalate depending on which load it supports.
It absolutely can. If the 24-volt supply is feeding critical safety systems like the electronic hydraulic power steering, the EHPS or the electronic braking system, the EBS, the safety goals must escalate to ASIL C.
And what does that mean in practice?
It means the design, verification, and component selection process is exponentially more complex and expensive. ASIL C, for example, typically requires component redundancy and error detection coverage above 90%, driving up both cost and development time significantly compared to a non-ASIL rated product.
Let's walk through the required hazard analysis and risk assessment, the ACRA scenario the sources provide, to really understand how ASIL C is reached.
The primary hazard example that dictates the ASIL level is DC-DC output over voltage. If the output stage fails and the voltage spikes above 32 volts, instead of the nominal 27.5, the consequence is immediate and potentially catastrophic.
What specifically happens at 32 volts?
Well, high current loads, like the headlights and wipers, could immediately burn out, leading to a loss of visibility, especially during site maneuvering. More critically, the EHPS ECU, sensing the dangerous overvoltage, is mandated to immediately shut down to protect itself.
Resulting in total steering assist failure.
Total failure.
So if we rate that scenario using the ASIL classification metrics, severity, exposure, and controllability, where does it land?
If we rate the severity S as S3, which is life-threatening injury risk due to loss of control, the exposure E as E4, high probability as the truck is always moving, and controllability, C as C2, difficult for the driver to correct sudden steering loss. The resulting matrix demands a safety goal of ASIL C.
So that analysis proves that OVP, over voltage protection, isn't just a feature, it's a mandatory core functional safety target.
It is?
To meet ASIL V or C, you can't rely solely on the software running on the main microcontroller, the MCU. What mandatory hardware safety mechanisms are required for this level of reliability?
Redundancy and independence are the guiding principles. First, a dedicated independent OVP circuit is mandatory. This is a separate hardware comparator circuit using its own voltage reference that operates entirely independent of the main MCU.
And what does it do?
If the output voltage exceeds 32 volts, this circuit must instantly and physically shut down the PWM control. The reaction time specified is less than 50 microseconds. That reaction speed is necessary to prevent component damage.
What other redundant controls are needed?
Second, an external watchdog chip must monitor the MCU's operation. If the MCU freezes or gets into an endless loop, the external watchdog triggers a hard reset or a safe shutdown. Third, we require redundant ADC sampling. This means the output voltage must be measured by two separate MCU analog-to-digital converter channels, and the software has to include cross-checking logic to detect and fault if a single ADC channel begins to drift or report erroneous data.
And what's the overall operating philosophy when a severe, unrecoverable fault is detected?
The requirement is for a fail-silent design. When the system detects a severe fault that it cannot safely mitigate or recover from, like a short circuit or an irreconcilable voltage measurement disagreement, it must prioritize system shutdown over continued, potentially dangerous, erroneous operation.
Better a complete safe power loss than providing a fluctuating, unstable voltage.
Precisely.
Let's pivot to EM-CMI countermeasures. High-frequency CMC switching is fantastic for size and efficiency, but it's notoriously noisy. How does the design ensure communication and radio systems aren't constantly interrupted?
Filtering noise is critical. The compliance goal is extreme, meeting CSPR 25 Class 3, or ideally Class 5, and ECE R10 Rev. 6. This prevents interference with everything from the CAN bus communications to the driver's radio and DIB reception. Achieving Class 5 with high-speed CIMP is a significant engineering feat.
So what is the required filtering strategy?
On the HV input side, a robust two-stage common mode choke, or CMC, filter is essential. Engineers typically combine specialized cores. Nanocrystalline cores are preferred for attenuating very high-frequency noise, and you combine that with ferrite cores for lower-frequency attenuation alongside carefully selected X and Y capacitors. The design also has to ensure all cables are shielded and that the housing acts as a complete Faraday cage.
And the PCB layout itself must be designed to minimize the primary source of that radiation.
This is absolutely fundamental with shielding. The design requires a multi-layer board, at least 4 or 6 layers, with a complete solid ground plane for maximal shielding. And crucially, the seam gate drive loop area must be minimized to the absolute physical limit. Since an MCTA switch is so incredibly fast, generating high DVDT, minimizing this loop area directly reduces the generated electromagnetic radiation. That is the key variable in passing stringent CSPR 25 tests.
I find the advanced technique of frequency dithering fascinating. Can you explain how this helps pass EMC standards?
Yeah, frequency dithering is an advanced trick used to manage the noise generated by the primary switching frequency. A DC-DC operating at a fixed 200 kHz, for example, generates a sharp, high-energy noise spike precisely at 200 kHz in its harmonics. If that peak exceeds the regulatory limit, the design fails.
So how does dithering mitigate that peak?
By introducing a small, intentional frequency variation, say plus or minus 5%, in the PWM control, you slightly spread that noise energy across a wider band. If you visualize the noise on a spectrum analyzer, instead of one tall, narrow peak, you see a wider, shorter hill.
Yeah.
This drastically lowers the peak EMI level while keeping the total energy the same.
And that strategic spreading of noise energy is often what allows high-frequency CCS designs to comply with those tight CISPR 25 limits.
It's a key part of the solution.
That covers the hardened structure and the complex safety architecture. Let's move to Section 7, the software, diagnostics, and the strategic path forward. The brain controlling this rugged box.
Given this operates in the heavy commercial vehicle ecosystem, the communication architecture has to strictly adhere to the industry standard. CAN 2.0b, utilizing the Heavy-Duty Vehicle Protocol SAE-J 1939-21. This standard ensures interoperability across all the truck systems, from the engine control unit to the instrument cluster.
What key data, the PGNs, does the DC-DC have to broadcast in real time to the vehicle control unit?
As an intelligent node on the network, the DC-DC has to constantly broadcast a defined set of data, these parameter group numbers, or PGNs. This includes critical operational data, actual output voltage, and current internal core temperature readings, detailed failure status flags for things like overvoltage, undervoltage, short circuit.
And crucially, its power derating status.
Yes, that's critical. If the unit gets too hot or detects a fault and has to reduce its output power from 5 kilowatts down to 3 kilowatts, the VCU needs to know immediately so it can manage system load and potentially alert the driver.
And for maintenance, standardized diagnostic support is essential.
Absolutely. Full support for the Unified Diagnostic Services, or UDS protocol, that's ISO 1429 on CAN, is mandatory. This allows dealerships and service technicians to perform standardized maintenance procedures. Reading diagnostic trouble codes with specific fault details, reading internal data identifiers like the part number or software version, and remote I/O control for specialized diagnostics. It just ensures fast, cost-effective troubleshooting.
Speaking of software, maintaining a mission-critical fleet component requires updating the firmware without bringing the truck into the shop. Over-the-air capability is essential, but it can also be risky.
OTA is essential for long-term fleet maintenance and security updates, but it absolutely must be done safely. This unit requires a dual bank, or AB partition, bootloader architecture. The concept is that the flash memory is divided into 2 banks. The current validated firmware runs in Bank A, while the new firmware is downloaded and installed into Bank B.
Which prevents a corrupt update from bricking the truck.
Precisely. Only after the new firmware in Bank B is completely verified, checked for integrity and security, does the system switch the boot pointer over. If that switch fails for any reason, the system safely rolls back to the known good firmware in Bank A.
And this all has to be secure.
This entire process must utilize secure boot, using cryptographic checks like CRC32 or SHA-256 validation to ensure only signed, verified firmware from the OEM is loaded. It protects against malicious injection.
Now for the final confirmation, validation and testing. We've described the brutal environment. Now we look at the torture tests designed to prove the DC-DC can survive 10 years and 300,000 kilometers.
The validation plan is exhaustive.
Right?
Electrically, we require rigorous dynamic load response testing. When the EHPS pump surges from 0 to 120 amps, the DC-DC's output voltage can't drop or spike excessively. It has to recover its stable 27.5-volt output in less than 200 milliseconds.
And what environmental tests are the ultimate stressors for the internal components?
The thermal shock test is the supreme endurance requirement for a high-power component. The unit has to undergo 1,000 cycles, transitioning rapidly between -40 Celsius and +85 Celsius. This cycling test is specifically designed to find fatigue failures in the thermal interfaces, the ceratome module solder joints, the internal bond wires, and the interface between the potting material and the PCB.
These thermal expansion and contraction cycles are the primary limiter of power electronics lifespan.
They are.
And how do they ensure the housing and ceiling survives that cement mixer environment?
That requires durability tests like 720 hours of continuous salt spray testing to ensure long-term corrosion resistance for the housing and connectors. We also look at the long-term durability testing designed to predict failure before it happens.
That's where the accelerated tests come in, right?
No.
Specifically HALT and HUS.
Correct. We require 2,000 hours of continuous operation at 80% load to confirm long-term thermal stability, and 100,000 power cycling tests, switching the load from 0 to 100% repeatedly to specifically stress the internal bond wires of the power devices. And then there is HOLT and HACES, highly accelerated life testing and highly accelerated stress screening.
That methodology is incredibly intensive. What do health tests reveal that standard tests would miss?
These tests involve pushing the product far beyond its specified operating limits, using extreme simultaneous temperature cycling, high-amplitude vibration, and rapid power cycling until the product physically fails. The goal isn't to prove compliance. The goal is to quickly find the design margins, identify the fundamental weak points, and ensure the product is structurally sound, highly reliable, and has sufficient margin before it ever enters a fleet.
Finally, we address the strategic decision for the engineering team, framed in the style of a high-level consulting recommendation. Do they build this highly complex, safety-critical system themselves, the make versus buy decision, or do they partner?
For a project of this complexity, especially in a specialized lower volume application like the cement mixer truck, the strong recommendation is to outsource or co-develop with an experienced Tier 1 supplier, at least for the first generation. This is really about risk and capability management.
I'm going to challenge that. If this component is truly safety critical and defines the core reliability of the truck, shouldn't the OEM want to control that technology internally?
That is the right question, and it comes down to the non-recurring engineering, or NRE costs, versus the capability gaps. Building this from scratch requires an astronomical, specialized investment. It means mastering SICKETOS, high-frequency design, complex magnetic component simulation, and crucially, building or accessing highly specialized, immensely expensive test infrastructure, certified EMC chambers, high-voltage test rigs, and dedicated health house equipment.
So the NRE cost for a relatively low-volume special vehicle segment makes internal development prohibitive, at least initially.
Exactly. The cost of achieving ASIL-C certification internally, combined with the risk of project delays due to technical complexity, is just too high. By partnering, the OEM can focus its internal resources on the overall vehicle control strategy, the VCU and BMS coordination, while transferring the core DC-DC technical development risk and NRE costs to a proven specialist.
What are the absolute critical criteria for evaluating those Tier 1 suppliers? How do you ensure they can deliver something that survives 5.8 grams and IP6K9K?
They must have a proven track record in heavy commercial vehicles, specifically with continuous outputs of 5 kilowatts or greater, and mandatory liquid-cooled DC-DC experience. Experience with passenger cars is insufficient because they simply do not face the continuous load or the 5.8 grams vibration profile. The supplier must also demonstrate a verified, mature ISO 26262 process capability and deep competence with CC high-frequency design, ensuring their product is optimized for the extreme reliability demands of this application.
We started by making the bold claim that the DC-DC converter in this heavy vehicle is not an auxiliary component, but a core safety unit. This deep dive has meticulously mapped out why that is true, examining the electrical, the thermal, the structural, and the safety requirements needed to survive the unique and brutal environment of a cement mixer job site.
The conclusion is unwavering. The DC-DC in the mixer truck is the invisible main power supply for the entire control network. and success hinges entirely on adopting the CT-Cure architecture for density and mechanical resilience, enforcing mandatory liquid cooling and extreme anti-vibration design, and building the entire architecture around a rigorous ACEL BC functional Hagee strategy.
It's a complete systems approach, and it really demonstrates the staggering engineering effort required for a single component in a niche-heavy vehicle. The fact that they're deploying technology previously reserved for the highest performance applications just to survive a construction site is telling.
It is a critical data point. The integration of high-performance, high-frequency 6i technology, used here specifically to combat brutal mechanical forces and environmental contamination, it suggests a fundamental shift in robust power electronics design.
So if the technology is being deployed this aggressively in a cement mixer, what does this tell us about the future of vehicular power electronics in general?
Our final provocative thought is this. If the efficiency and reliability gains of SECSI, combined with these mandatory ASIL-C and IP6K9K durability standards, are now the baseline requirement for making a rugged commercial vehicle dependable, how quickly will these extreme durability standards trickle down? Will the push for reliability and fuel economy force even the simplest power supplies in all mass-market electric vehicles, passenger cars, delivery vans to adopt similar, highly ruggedized, SECSI-based architectures? The concrete mixer might just be laying the groundwork for the next generation of absolutely dependable automotive electronics.
Food for thought, indeed. That's all the time we have for this deep dive into the safety-critical heart valve of the hybrid heavy vehicle. Thank you for being our expert guide through this punishing technical specification.
My pleasure.
And thank you for joining us. We'll see you next time.